how to calculate pH from a buffer solution, and what we do today and how I work through that today is exactly how you'll need to work through it on the exam. So make sure to pay attention, take really good notes. I'm not saying it'll be the exact same buffer, the exact same numbers, but the exact same way to solve it for sure. So what is a buffer? It is a combination of substances in a solution that act together to resist changes in pH. Okay. Now, the purpose of a buffer is so that when you have things added to the solution, pH does not wildly change. Okay. We know acids, we learned how to calculate pH. We know that acidic things, they lower pH, and things that are basic, strong bases, they raise pH. But a buffer has components in place so that nothing changes pH. Ultimately, nothing changes it much. It might fluctuate a little bit. Why are buffers important? It's important to maintain proper pH in biological systems. Okay. The main aspect we're going to talk about with that today is your blood. Your blood has a pH that it has to maintain a very constant pH. So that's one reason it's important. But there's also other reasons. We also use buffers to maintain pH in laboratory solutions. Hospitals have labs, clinics have labs. So these things, people are constantly, have you ever wondered how many of your hours of your life you like sat at a stoplight or spent in the grocery store or whatever? I've wondered how many hours of my life I spent standing at a pH meter checking pH on solutions in grad school. I don't want to know actually, but I've wondered. A buffer system is usually a weak acid. So this is what a buffer is. It contains a weak acid and its conjugate base. A buffer system contains a weak acid and a conjugate base. Okay. So I want you to look at these. We've talked about conjugates. We practice labeling them, and I want you to look at these two reactions at the bottom of the slide here, and I want you to label what is the conjugate acid, or sorry, I'm going to say that backwards so many times today. What is the weak acid and what is the conjugate base? Which component? The first equation is very generalized, and the second equation was with acetic acid. All right, so you should have for the first equation, this right here is the weak acid. And we know once an acid gives away the hydrogen ion, what's left over is the conjugate base. Okay, so you should have that for the first one. For the second one, somebody tell me what the weak base is. Is it the first reactant or the second? Water, acetic acid or water? Any guesses? Well, no, Meredith. Good guess, though. You had a 50-50 shot. Sorry. The weak acid is acetic acid. So water is playing the base here. How do we know? Because water accepts, here's the acidic hydrogen on, oh, she thought I said base, everyone. No, I believe you, Meredith.
I think you accidentally did say base.
I did?
Yeah, I was because I was thinking the same thing.
Yeah, you did say base because I was thinking water.
I promise I have my coffee, okay? This is like that one time my computer was on silenced, remember? And I was like, can anybody hear me? I can't hear y'all. Why can't I hear y'all? I think you need to turn your volume. Yeah, that was me. I'm the problem. Just ignore me. I'm just kidding. All right, so the weak acid, rather. is acetic acid, and the conjugate base is going to be acetate. Okay. There we go. Okay, so as long as you can label those components, you're good. So we're going to draw a diagram to show us how buffers respond, what little reactions take place, so that when things like a strong base or a strong acid are added to a buffer solution, how they are neutralized. Okay, if we can neutralize something, here's an example of something being neutralized. OH plus H. These things can change pH. Do you remember the relationships we wrote? I'm going to scroll up for just a second. Right here, do you remember these? They're in the video, so I don't think I actually went over these Tuesday. So if you haven't watched the video, then no, you don't remember these. But if you have, these relationships, I don't think we got to them Tuesday. If we raise pH, we have a lower amount of H plus. As pH goes up, H plus goes down, OH minus goes up, okay, concentrations. So, and then vice versa. If pH goes down, then you have a lot of H plus around, very little OH minus. So keeping that in mind, these things can change pH. How do they neutralize one another? They come together and they make something that cannot change pH, something that's very neutral, something that's not going to increase or decrease pH, okay? So if we can neutralize anything that's threatening to change pH, then that's essentially what a buffer does. So let's say we have some sort of weak acid, and it is in equilibrium with a conjugate base. Remember, you cannot do these with strong acids or bases. It has to be a weak, you have to have an equilibrium. Let's say that we add a strong acid. Anybody want to tell me an example of a strong acid? Pick your favorite. Y'all, this is a rough day. Dakota said, why is it H minus? It should not be H minus. It should be. Now my eraser is not going to work for us. It should be H plus and OH minus. Forgive me. I need to slow down. All right. If we add an acid, let's say we add HCl. I'm just going to start acids down here. If we add HCl, HCl is a strong acid, right? HCl is going to dissociate into H plus and Cl minus, and it is the H plus component that can change pH. The more H plus we have, the lower pH goes. So if we have H plus, I want you to look at our buffer right here. Which component, the weak acid or the conjugate base, do you think could react with H plus, bind to it, and neutralize it? Which component do you think is more likely to do that? Any guesses? You got a 50-50 shot. The weak acid or the conjugate base? Which component is going to pick up that H plus and neutralize it?
The conjugate base.
Yes. Look at this. We have an electrical attraction even. A conjugate base is negatively charged. Weak acid is neutral. So because this H plus has a positive charge, it's even attracted to that positive charge. So what's going to happen is this will kind of swoop down the way we draw it. It'll bind that H plus, and they'll just make more of the weak acid. The weak acid right here has no power to change pH. Weak acids in and of themselves, acids in general in and of themselves, the molecule that's not disassociated will not affect pH. It's when it disassociates and when it gives off an H plus, that's when it can change pH. So just making more of the weak acid, you've made something that's been neutralized, not going to change pH. All right. What about a base though? If we add a base, a strong base, the strongest one we know is OH minus. Okay, what's going to happen if we add some OH minus? I want to scoot that over. What's going to happen if we add some OH minus, some hydroxide? Hydroxide is threatening to raise the pH. I have to be careful what I say. What could neutralize OH minus?
Would it make water?
Yeah, how? How would it make water?
You would take the hydrogen from the HA,
Boom. Yep. So this guy is going to disassociate, and it's going to make some H plus, and what's left over is it's going to make more A minus, right? And OH minus and H plus will make water. And water is definitely powerless. If you write on my eval that I can't spell, or that I can't talk and spell at the same time, I won't be surprised. There we go. Okay, so that's essentially, here's a simplified, kind of a cleaner version of what we just wrote. This is the buffer diagram I was talking about. And it just is a reminder. It's a simple thing that I think helps you remember how a buffer works, how it combats an acid or a base so that things, nothing changes pH. Questions on the buffer diagram? I want you to be able to write it out, explain it if you have to. All right. So let's kind of, here's a couple questions to just really think through, just different style questions to just help you kind of get your feet underneath you with buffers. So look at this right here. We have acetic acid and water makes the hydronium ion, and it makes the acetate anion. And here's the weak acid. And here's the conjugate base. All right. Now this first question says, what happens to pH if we add NaOH to water? So we don't have a buffer in place yet. We just have a solution. Well, not even solution. We just have pure water. And from your understanding of bases in water, what's going to happen? You can write out our chemical reaction if you want and look at the products and then answer the question. Or if you can imagine it in your head, then you can tell me what's going to happen to pH. Will it go up or will it go down? If you want to draw out the chemical reaction, we know we have NaOH, which is going to disassociate into Na plus and OH minus. And it's the base here, OH minus, that is going to, these lone pairs on this oxygen are going to grab a hydrogen off water. This looks really redundant, but it's going to make H2O when it does that. What's left over from water is going to be OH minus, and then we'll still have the sodium ion floating around. And this guy right here is what can change pH. We'll create hydroxide, and pH will go up because there's nothing in water that can neutralize OH minus. Or when it does, it creates more OH minus. All right, look at the second question now. Now what happens to pH if we add sodium hydroxide to the above reaction? Okay, this one up here, at equilibrium. What will happen to pH? So if we add sodium hydroxide, it's like adding Na plus and OH minus. What's going to happen? What portion of this reaction up top with the star by it is going to react?
H3O.
H3O, any other thoughts? The portion that will react is the stronger acid. So you know what? This has a plus charge, looks kind of acidic. It could totally give a hydrogen away. We also have a weak acid over here. If you look at your acid base table and you see which one's stronger, you're going to go with that acid. But also too, this right here, these two components are the buffer components. You got to pick a component from your buffer that's going to react and neutralize. And if that's the case, then it's the acetic acid. Acetic acid, here's our acidic hydrogen. And these lone pairs, one of the lone pairs on oxygen will grab that hydrogen. It will neutralize OH minus, will make water, and then we will have the acetate anion, and we'll still have the sodium cation floating around. And I will not count you incorrect if you tell me NaCH3COO, sodium acetate. Either one is acceptable. So because of that, what's going to happen to pH? Well, essentially what we're going to say is that acetic acid will neutralize the NaOH, and pH will not go up. That's what would happen. And when we work a buffer problem, you might see that pH fluctuates a very, very small amount. So when we say it's not going to go up, we mean it's not going to go up drastically. It might go up like 0.1 or 0.05. But that's a pretty good buffer if it's keeping the pH within 0.1 or 0.05 of its original pH. Okay, now what happens to pH if we add HCl to the above reaction at equilibrium? So we have HCl. Which component of this buffer system up here, this one or this one, will react with HCl? The weak acid or the conjugate base? Anybody? Weak acid or conjugate base? What's going to neutralize? What has the ability to neutralize HCl? Conjugate base. Yes, the conjugate base. CH3COO minus, because this is going to disassociate. We'll snatch up that H plus, react with bind to the acetate anion, and we'll make more of the weak acid. And we'll still have that chloride anion floating around. So the conjugate base will bind the H plus, and really you could say by binding the H plus, what we mean is it will, that's, if I say the word neutralize, or if you were to tell me it will neutralize the acid, that's a better word than we'll bind or we'll pick up or whatever, the H plus. It'll neutralize it, and pH will not go down. All right, any questions on these? Okay. All right, well, we're about to get into some math, so turn your math brains on, grab your calculator. Here's how we're going to calculate pH of a buffer. And what I'm about to show you, well, let me just read this real quick. We can find the pH of a buffer solution if we know the concentrations of the weak acid and conjugate base, all right? So here's a chemical reaction for a weak acid with water, just an aqueous solution, what it makes. And we know, because there's an equilibrium set up right here, the double arrow indicates that to us, that we can write Ka. You guys remember on Tuesday, we wrote out equations for Ka. And we learned how to, well, just how to write those out for weak acid. And then we looked at a table with different Ka values. I'm not going to derive this for you, but basically we can do some math magic on this, and we can turn it into this equation over here, which is called the Henderson-Hasselbalch equation, okay? And as you can see, this equation is letting you solve for pH. Now, I'm not a yeller, so I'm not going to yell, but I would want to emphasize right here, this equation is only for buffers. We have other equations to solve for pH, right? Can you think of them? We have pH equals the negative log of H plus. We have pH plus POH equals 14. You could rearrange that to solve for pH. We have lots of equations. And here's what's going to happen on the exam. People are going to be, I'm going to ask you to solve for pH of something. And you'll be like, how do I know which equation to use? There's freaking 3 equations that have pH in them. And here's what I'm telling you. The Henderson-Hasselbalch equation is only if I specifically tell you in the problem that it is a buffer. If it does not say buffer anywhere in the problem, do not use Henderson-Hasselbalch, okay? You'll get real confused real fast. Use one of these other 2 over here. Don't use, it's only for buffers, all right? Now, if we look at this equation, what does it say? It says pH equals what? It equals pKa. What is pKa? Well, we're going to learn how to solve for pKa in just a second. And then it says, but it equals pKa plus the log of A minus, we know that's the conjugate base, over HA, which is the weak acid, concentration of the weak acid, concentration of the conjugate base. Now, I'm going to tell you what pKa is, but also one thing to point out, you're so very used to doing negative log. Okay, on Tuesday, that's all we did. We said pH equals the negative log of H plus, and it does. But in the Henderson-Hasselbalch equation, we're adding, it's plus the log of. So you should have this equation. I'm going to put it on your exam 4 resources page. Just pay attention when you're writing it out. Don't get things mixed up, okay? All right, so what is pKa? Well, we know that pH is the negative log of H plus. POH is the negative log of OH minus. So pKa is, guess what? The negative log of Ka. Any Ka value that we have, we can go up to that table. There's like 10 or 15 Ka values on the table for weak acids. You can pick any one of those out. You just plug it in. You take the negative log of it. That is pKa. All right. And now we are going to talk about qualities of a good buffer. So, number 1. First off, I've already said this, but first quality is that you have a component or a system that has a weak acid plus a conjugate base, okay? Do not ever tell me that you can have a buffer with a strong acid or strong base, okay? Secondly, a buffer is good or strongest when it contains roughly equal amounts of weak acid and conjugate base. You want roughly equal amounts. I don't really watch TV, don't really watch sports, but I do know how football works. Anybody watch football? Anybody diehard football fans? Well, if you don't know anything about football, that's okay. In football, you have an offense and a defense, right? At least hopefully you know that. And looking at this equation, well, hold on, stay with football for a second. The offense and the defensive team, you can only play 11 people at a time on the field. And so you need 11 people on your defensive team and 11 people on your offensive team that can play at a time. You need equal numbers is what I'm trying to say. That's when the team works the best. That's when it's the strongest. So the same way, if this is our offensive side and this is our defense, if we have 100 of these molecules, guess what? We need 100 of these, okay? That's when a buffer is the best and the strongest, when you have equal amounts. That way it can react with or neutralize whatever is thrown at it, okay? It's my one sports analogy for the day, for the semester. All right. What this means is that the buffer is the strongest when the pH of the buffer is about equal to the pKa. I'm going to prove that to you here in just a second. When it's being kept at a pH that is roughly equal to or approximately equal to the pK. Grab your calculator really quick, and I want you to type into your calculator the log of, and I want you to on top, like on the top number, I want you to put in, I don't know, pick 100, and on the bottom, divide by 100. Do the log of 100 over 100, or I don't care what number you pick, just do the same on the top and bottom. Do the log of, and then do a fraction with the same number. 1 divided by 1, 10 divided by 10, 20 divided by 20. What do you get? You get 0, okay? The log of any number divided by itself is 0. And what that means, when you have the same numbers on your offense and your defense, or the same number of weak acid and conjugate base, this whole term goes to 0, and guess what? pH equals pK. That's what's left. So the buffer is the best when you have roughly equal amounts, equal concentrations of weak acid conjugate base, and therefore pH, the buffer is the strongest when the pH of that buffer is made to be right around the pK of the weak acid. And then lastly, another good quality is that the molar amounts of, this is the weak acid, HA, and conjugate base, A minus, are in about 10 times excess. I'm going to write 10x. 10 times as concentrated the amount of acid or base that is added to the buffer. All right, that was a long one, but a good quality of a buffer is when your molar amounts of weak acid and conjugate base are about 10 times as concentrated as any strong acid or strong base that you add to the buffer, okay? Which makes sense. You want to have a lot of your buffer components in place. That way, if you add a strong acid, you have all the conjugate base molecules present that you need to neutralize it. If you add a strong base, you have all the weak acid molecules present that you need to neutralize anything and everything that's added. Okay, so I should hope that you could be able to explain these qualities to me, list them if you had to, identify them on exam 4. All right, it says, next question. We're actually going to look at how to calculate pK. I have a poll question for this, so I'm going to read you the question, and then I'm going to kind of let you do it. I'm going to try to let you figure it out. We'll go back and we'll answer it, but give it your best shot. It says, you want to prepare a buffer solution with a pH of 5. Which acid and its conjugate base should you use? So remember 3 here. You want the one where the pK is the closest to pH. So look at these that you're given the Ka value of all of these. I'm going to go ahead and launch the poll question, and you want to put your answer in the poll. Formic acid, acetic acid, propanoic acid, ascorbic acid. So think about how to go about this. What do you need to do to Ka? You're going to need to calculate something for all of them and then choose the option. Had almost 2 minutes. Give me another 15 seconds. If you have no idea what to do, just give me your best guess, and then we'll talk through it. All right, it's been 2 minutes, but we're only 64% voted. I'm going to end the poll, and then we're going to look at how to work this, okay? So if you haven't voted, it's okay. Share results. All right. How do we do this? Well, we want to know which one has a pKa that is closest to a pH of 5. So we got to calculate the pKa of all these. How do we do that? We just take the negative log of all of these. So what did y'all get when you calculated the negative log for formic acid? The most voted for answer was acetic acid, so we'll see if that's the closest. What do you get when you do the negative log of 1.8 times 10 to the minus 4? Kenethia said 4.7. That's a 4. Okay, what about acetic acid? .8. Okay, that's pretty close. What about propanoic acid? Wait. Yeah, I think we're off here. Wait, Kenethia. Kenethia, are you telling lies?
Wait, it's the 4.8 for the propanoic acid. I did my numbers messed up.
That's right. What was it for formic acid? I think this one's 4.7. Formic, the first one.
I messed up.
Yeah, 3.7.
4.
Okay, what about ascorbic acid?
.1.
Okay. So acetic acid was close, and most people picked acetic acid. But propanoic acid is even closer. So the buffer you would want to pick would be this acid and its conjugate base. Does that make sense? How you calculate a pKa? How this plays into the quality of a good buffer? All right. Okay, so with that, we have arrived at a buffer problem. So look at this, 1 slide, 2 slide, 3 slides. It's a 3-part problem. The first part of every problem is I want you to calculate the pH of a buffer. So I say, what is the pH of a buffer solution? And here's your components, 0.1 molar HF and 0.12 molar NaF. Now, it may not be the same components every time. I could switch up the weak acid and conjugate base components, but I also will give you the Ka, or at least you can look on the table if you have to find the Ka of a weak acid. So we need to identify first, which one's the weak acid, which one's the conjugate base? Is NaF the weak acid or is HF the weak acid? Remember, to be an acid, you have to have a what? You have to have a, okay, Dakota's HF, yeah. You have to have a hydrogen, okay? They're proton donors. You can't be a proton donor if you don't have a hydrogen, which is a proton as an ion. So this is the weak acid, which makes NaF the conjugate base. And the reason we had to get that straight is because that's going to tell us what goes on top and what goes on bottom. We're going to plug in the concentration for HF here on bottom, the concentration for NaF on top. Okay, it's the number one way people screw this up is they flip that. Now we got to calculate, we have Ka, we got to calculate pK. So the first step is 1, identify the weak acid and the conjugate base correctly. 2, calculate pKa, which is just the negative log of 3.5 times 10 to the minus 4. And I think, what do y'all get? It was like 3.46. Surely my memory's not that good. I feel like our memories are really getting bad in the day and age of iPhones. I used to have like 10 phone numbers memorized or more. Like your grandparents' phone numbers. I don't have those memorized anymore. What'd y'all get for the PK? 3.4. Do you have another decimal? Can you give me one more decimal? I like 2 decimals here. I think it's 4.6. All right, so now we're going to plug everything in. Yeah, there you go. Now we're just going to plug everything in. So pH, here's the Henderson-Hasselbalch equation. We're just going to plug in pKa, 3.46, plus the log of, top is the conjugate base, so that's 0.12 molar. On bottom is the weak acid, 0.1 molar. And then you just put all this in your calculator. What do you get for pH? Anybody got it? 3.54. Okay, thanks, Dakota. And that's it. That's done with the first part of the buffer problem. Okay, on a scale of 1 to 10, how hard was that? There's a few steps. Is that crazy hard? I hope not, because it's about to get a little bit harder. Now, I will tell you, the buffer will not change. It will be the same through all 3 steps of a buffer problem. So here we have HF and NAF. That's going to be the same, which means your pK is also the same. So we'll come back and we'll get this value when we need it. Now, we're going to add some strong base. Think about that buffer diagram. What is going to happen? We're going to add some strong base. So we have HF in equilibrium with F minus. What's going to happen when we add strong base? What's going to neutralize that strong base? NaOH is going to make Na plus and OH minus. And this weak acid right here is going to donate the H plus, and those two are going to go off and make water, and then we will inherently make more F minus. That's how we're going to neutralize NaOH. So the concentrations of these things, we know the initial concentrations, but they're going to change. We're going to use up some of our weak acid, and we're going to make more of our conjugate base. So guess what? The concentration of this is going to go down. We're going to need to use some of it, and we're going to make more F minus. So the concentration of this is going to go up. The way I like to remember this is when you add base, you add base. Okay. So we need to recalculate the concentration of our weak acid and conjugate base before we go and plug it into our equation up here so that we can see how pH changes, hopefully minimally. And to do that, it says that we add 0.02 moles of NaOH, and it says that we have 0.1 molar and 0.12 molar NaF. If you notice the units here, moles and molarity are not the same. Molarity is moles per liter. Right now, we just have moles. So step number 1 is to calculate the molarity. Okay, calculate M of whatever you're adding. Here it's NaOH. That is going to be equal to the number of moles, 0.02 moles, divided by liters. How many liters do we have? We just have 1 liter, right? So we're going to divide by 1. I made the math easy here. I promise I won't make it that easy on the exam. I'll probably tell you like 800 milliliters or 500 milliliters or 1.2 liters. So the molarity is just 0.02. Now we can write molar. So do not think this number will always equal that number. But here it does. All right. Now we're going to make what we call, we're going to make what we call an ice chart. Anybody heard of an ice chart? In an ice chart, we are going to write down I stands for the initial concentrations. C stands for change in concentration. E stands for the new equilibrium concentrations of what? Of the weak acid, here it's HF, and the conjugate base. So let's write down what were the initial concentrations. They're given in the problem. The initial concentrations are right here, 0.1 molar and 0.12 molar. I'm going to write those in, 0.1 molar, 0.12 molar. Now, how do the concentrations of these things change? Well, they're gonna react over here until we have no more OH minus. We're gonna decrease our concentration of HF until we run out of OH minus molecules to neutralize. And we're gonna increase the concentration of F minus until we run out of OH minus molecules. Well, how many of those do we have? We have 0. This was the molarity of NaOH. So we have 0.02 molar. And remember the downward arrow over here, right here for HF, means that we're going to decrease that amount. So we're going to subtract from this column. We're going to lose 0.02 molar. And the upward arrow indicates that we're going to add 0.02 molar to the conjugate base. Now we're just going to recalculate new equilibrium concentrations. Okay. Is everybody with me so far? Questions on what we have done so far? Now what's the next step? Now we just take our new equilibrium concentration. So this last row right here, we're going to plug these into the Henderson, I'm going to abbreviate, Henderson-Hasselbalch equation. So that is up here, right there. We're going to take that, and it says pH equals pK. What was our pK? We calculated it right up here. There it is, 3.46 plus the log of the concentration of conjugate base, which is 0.14 molar. Remember, F minus, or sodium fluoride, is the conjugate base. And weak acid is now 0.08. Okay. And don't get confused by the fact that I'm just writing F minus here. Remember, sodium is just a spectator ion the whole time. Anytime you have a little group 1 or group 2 metal attached, that cation is just a spectator. It's really the F minus that's the player here. That's the part that can neutralize any acid that we add to the buffer. What's our new pH? So do 3.46 plus the log of 0.14 divided by 0.08.
Okay, I don't want to feel dumb for asking this, so please don't judge me.
No judgment.
Okay, how do you go from 0.1? I know you use the negative 0.02, and then you got 0.08.
Uh-huh.
How did you just
This should essentially be like 1, 0. So it's like saying 10 minus 2.
okay? Yeah.
You're good. I wrote stinking H minus and OH plus earlier, okay? So no one can laugh at you for that question. 3.7 is what Kenethia got. Is that right? So you see that pH initially was what? 3.54 when nothing was added. And then when we dump in some really strong base, like really strong base, our buffer kept the pH at 3.7. That's pretty good. It only changed by 0.15 or 0.16, I guess. So not bad. It went up a touch, but that's pretty consistent. So now we are 2/3 of the way done. This is a hard problem, isn't it? So guess what? It's probably going to be worth several points on the exam. At least, got to be worth at least like 15 points. But this is fine. You should know how to do it. Okay, now look, we're going to add 0.02 moles of HNO3. We're going to add some acid. So remember the first thing we got to do, number 1 up here, what did we do? We calculated molarity of the base. We got to do the same thing here. Let's calculate molarity of the acid. Now, I was very kind in the example problem because it's brand new. I did not change the numbers. I said we added the same amount of acid, 0.02 moles. But I could have easily said we add 0.04 moles. I could have said we have 0.5 liters, okay? So whatever the moles and whatever the liters are, it shouldn't matter. We still got to calculate molarity. So let's do that. Number 1, molarity of HNO3 is going to be equal to 0.02 moles. Molarity is moles of your solute divided by liters of solution divided by 1 liter. So the molarity equals 0.02 molar. Number 2, and this is for HNO3. We're going to make the ice chart. And we've got the weak acid and the conjugate base. The initial concentrations do not change. They're the same both times, or actually all 3 times. But we need to figure out how much are they going to change. Remember when you have a strong, this is a strong acid, so this is going to disassociate into H plus. I'm going to write the other part first, NO3 minus and H plus, okay? How will the buffer respond? Here's our buffer. Can we do a problem where you have the numbers like you would on the exam? Yes, we can. There's one in your textbook, I believe, that I'm gonna give for an example, and I think the answers are in the back of the book. And on review day, the day before the exam, I will for sure work a problem where the numbers are not the same. But the steps, Kenethia, are the same. Just because that changed the numbers, honestly, it should not make it any harder. Because all you do is you still plug in the number of moles that I give you, and you plug in the volume that I give you on bottom. You just plug those in and calculate molarity. So even if they're different, it should make the problem no more difficult. You're still going to calculate molarity. Okay, but on review day, yeah, I can work one like that. We probably won't have time today by the time we get done with this, but or if you want to set up a Zoom with me, I could walk you through one. All right, remember, it's the conjugate base. If we have some H plus free floating around in solution now, thanks to our strong acid that we put in, this conjugate base is going to snatch that up. And we're going to make more HF. So the concentration of this is going to go up. And we're going to use up some of our conjugate base. So the concentration of it is going to go down. We're going to need it. We're using it. So this tells us what to do to the column C or row C. We're going to make more HF. So we're going to add there. We're going to use up the conjugate base. So we're going to subtract there. So Dakota said, in these problems, are we still using molarity as a conversion factor? No, we're not using molarity as a conversion factor. We're not converting between moles and liters. We're just using moles and liters to calculate molarity so that when we do this math right here, when we say 0.02 molar, see how the units are the same? Okay, these units have to match, okay? If they don't, that would be like, well, here's what a lot of people do. A lot of people would write in 0.02 moles. 0.02 moles. That's what they'll do. But moles and molarity are two different units. That's like you trying to add milligrams plus milliliters. You can't add milliliters to milligrams. You can add milligrams to milligrams. Does that make sense? Does that help? Okay. Yeah, so just make sure we're not converting. We're just trying to get things in the same unit so that we can add and subtract them. All right, now recalculate your new equilibrium concentrations, 0.12 and 0.10. And these are what you're going to plug in to Henderson-Hasselbalch equation. So that is pH equals, is right up here if you need it. pH equals pK. What's our pK? Well, it has not changed. It's still the same as the previous problem. So 3.46. And remember, we calculated that in part 1 of the buffer problem. So you always got to go back and get your pKa plus the log, what goes on top, what goes on bottom. Concentration of the conjugate base, which is F minus. So this one, 0.1 this time is going to go on top, and 0.12 is going to go on bottom. What do y'all get for the new pH?
Hey, I have one more probably dumb question.
No dumb questions here.
Okay, how do you know if you add or like subtract? Is it about the conjugate base and weak acid, or apparently Kinesia needs to figure that out too? Because I've seen her like, yes. I
Yeah.
was just curious.
So you see these little, I'm going to color, you see these little arrows in green now that I'm drawing?
Yeah.
You remember when I walked through that? I don't know, I can re-explain if I need to. But we're asking ourselves, okay, if we're adding a strong acid, HNO3 is a strong acid, how will the buffer respond? Which component are we going to use up? Which component are we going to make more of? And when we add an acid, we're going to add acid. We're going to add to the weak acid column. And remember up here, we wrote, when we add base, we're going to make more, or we're going to add to the concentration of our conjugate base. So if you can remember that little motto, when you add base, you add to the base. When you add acid, you add to the acid. Okay, that will keep it straight what your signs are on these columns.
Okay, thank you.
Does that help?
Yeah, that helps.
Okay. Great. No, that's a great question, because that is one of the #1 things people do. Either they'll put the wrong they'll flip the concentrations when they plug them into the equation, or they'll get these signs wrong. They'll plug in plus and minus the wrong way. There's all sorts of little ways. But anyways, okay, so you see the overall pH dropped a little bit. That's what acids do, but not by a lot. This was a really strong acid that we added, and the buffer kept it relatively, I think it dropped by like 0.08. So that's pretty good. All right, now with the last 12 minutes we've got to talk about buffers in the body. So we probably won't get to the slides at the very end of this on titrations. I think we got about 4 or 5 slides left, and that's it, maybe 3. So that's the end of how to work a buffer problem. We will have one of those on the exam, okay? All right, let's talk about buffers in the body. 3 main buffers in the body. We got proteins can act as buffers. They can give away or receive hydrogens. You've got almost 60,000 proteins in your body, so that's a lot of different ways that they can act like buffers. They can neutralize acids or bases. They're not the dominant thing we think of as buffers, but they can act like them. Okay, phosphate buffer, this is in your cells, okay? This is your weak acid. And this is the conjugate base. And this works to maintain the pH of your cells, which is quite a bit higher. I can't remember if it's up around 10. Anybody a biology nerd? You remember what pH in your cells is supposed to be? But it's definitely higher than your physiological pH, okay? But this is the one we're really going to hone in on, bicarbonate buffer, okay? Do you guys remember your polyatomic chart? Think all the way back to the dinosaur ages, the first week of class, when we had our polyatomic chart. Bicarb was one of those polyatomic ions on there that I wanted you to memorize. It's very important. Okay, so carbonic acid, H2CO3, gives away a hydrogen ion, and what's left over is bicarb. And this is the conjugate base, and this is the weak acid. Now it's very, very weak. And in fact, it's so weak, it can even decompose another way. It can make CO2 and water. So there's actually 2 ways it can break down. It can break down to make bicarbonate plus. It can also break down to make CO2 and water. So we have a really unique situation here where we have like 2 equilibrium systems, 1 and 2, all within the same reaction. All right. So we haven't seen something like that before, but this can happen. And this is how our pH is maintained in our blood. Anybody know what physiological pH is? What your blood pH should stay around? It's a range. It stays within like 7.35 to 7.45. And our bodies have to be real good at keeping it there. So let's talk about how some things that can influence this and how it can change. Well, number 1, breathing can change blood pH, believe it or not, and our kidneys can also function to control and regulate blood pH. Let's see how they work in tandem. So changes in respiration. How does this affect blood pH? Well, you can have conditions called respiratory alkalosis, meaning based on how our breathing fluctuates or changes. Alkalosis means our pH is too high. It's too basic. Okay, so maybe it gets above 7.45. You can also have respiratory acidosis, meaning due to our breathing, our blood pH has dropped below 7.35. And how that can be corrected? Shifts in equilibrium. I'm going to abbreviate EQ. And changes in kidney function. Can help regulate and correct our blood pH if we have those situations arise. All right, guess what though? Changes in kidney function can also influence blood pH. Anybody know somebody, have a family member, or just know someone who's experienced some kidney failure? I have a family member currently who's maybe close to 60% kidney failure. So hopefully she'll get some medical help. But this can be corrected by, again, shifts in equilibrium. and changes in respiration. So we're gonna look at how equilibrium shifts based on our kidneys and our breathing. So you guys remember Le Chatelier, our good friend Le Chatelier's principle? Don't forget how that works, because that is everything we're about to talk about is going to require you to understand and remember how Le Chatelier's principle works, okay? So review Le Chatelier's principle if you need to. Before we move on though, other things can also affect pH. Our diet, things that we take into our body, different foods, different foods. There's very acidic foods, foods that are not so acidic, different medications that we take, okay, different pharmaceuticals can all affect blood pH. All right, so I'm going to pose a question here. What happens to our blood pH if we hyperventilate? And we're going to start just by looking at this picture over here where the lungs are. If we're hyperventilating, okay, are we increasing or decreasing respiration? Hyper means we're increasing. We're breathing really fast, okay? Like if you just got done running, or if you see one of those tarantulas that I showed you a picture of earlier this semester, that would cause me to hyperventilate, all right? So we're gonna breathe fast. What's gonna happen to the concentration of CO2 in our body? If we're breathing really fast and we're exhaling a whole lot, what's gonna happen to CO2 in our body? The concentration of CO2, we're breathing it out at an elevated rate. We're breathing in and we're breathing more CO2 out more quickly. So the concentration of CO2, if we increase respiration in our bodies, in our blood, what am I writing? We're decreasing CO2. Okay. So that's the first thing that's going to happen. We're going to reduce the concentration of CO2 in our body because we're exhaling very quickly. Now, according to Le Chatelier's principle, what happens if we decrease CO2? If we take away CO2 as a reactant here, right? It's on the left side. How would equilibrium shift to correct for that? You guys remember? If you take away a reactant, what does Le Chatelier's principle say? Equilibrium will shift right or left. It will shift to replace the thing we're taking away. It wants to replace it. So it wants to make more CO2. And the way you make more CO2 is you take these things, react them together, make more of this, and shift everything this way. So equilibrium will shift left. When that happens, look at our products. What is the one thing, the one item in this whole reaction that can directly affect pH? Is it CO2? Is it water? Is it carbonic acid? Is it bicarb? Or is it H+? What directly affects pH? This guy right here. Remember the relationships we wrote? If you increase the amount of H+, you decrease pH. Vice versa, if you decrease the concentration of H+, you raise pH. Okay, these are key. Remember these. So if we shift equilibrium left, what's going to happen to the concentration of H+ in our blood? It will go down. We're using it to shift equilibrium left. And when that happens, pH is going to go up. So the ultimate question here, what happens to blood pH if you hyperventilate, will raise blood pH. Okay? So it's kind of like a little shorthand code we just wrote. I totally want you to be able to write this for the exam. We only have a couple minutes left and we got 3 more questions to get through. So I'm going to kind of move a little more faster through these next 3. But if you need to go back and rewatch it, I'll post the video tonight or tomorrow in the morning. All right, what happens to blood pH if you hypo? So if we're decreasing respiration, that's hypoventilation. We're going to keep more CO2 in our body. We're not exhaling it as fast. So we're going to have a buildup of CO2 in our body because we are not exhaling very quickly. We're slowing down our breathing. In that case, guess what? If we have a lot of CO2, a buildup, Le Chatelier's principle says equilibrium will shift towards the right to use it up. If we shift everything right, all the way right, what's going to happen to your concentration of H plus? So equilibrium will shift right. What's going to happen to the concentration of H plus? We're going to make more of it, so it will go up. And if H plus goes up, we said pH goes down. All right, any questions on that? All right, last 2 minutes. What happens to your breathing rate? So now we're not asking about blood pH, we're asking how will our breathing change? Well, would we hyperventilate or hypo if our kidneys can't store bicarb? Uh-oh. If we need to store bicarb, so if we get a buildup of it in our blood, which means in this scenario, we're saying we have too much HCO3 in the blood. And we need our kidneys to store it, but it can't. Well, fortunately, we could shift equilibrium this way to reduce the amount of bicarb in our blood. If we shift equilibrium towards reactants, we'll use up some bicarb, we'll react it with H plus, and will help maintain a healthy amount of bicarb in our blood. So equilibrium will shift left. If that's the case, if we have a buildup of bicarb in our blood, equilibrium will shift left. What would that do to the concentration of CO2? If we shift towards reactants, we're going to make more CO2. So the concentration of CO2 would go up. When you shift left, you make more reactants. And if we have a buildup of CO2 in our blood because our equilibrium shifted left, how could our breathing respond to restore that, to fix that? Well, if we have too much of it, we could get rid of some by breathing out more heavily, by exhaling it. So if we would increase respiration, that would help in this scenario. So we would hyperventilate. Whoops. Last one, because we're at time. What happens to your breathing rate if you okay, this one's random. Accidentally inject yourself with NaOH. Don't do that. All right, real quick. NaOH, the one thing in this reaction, I'm going to key in on H plus. NaOH will make this. And these two things are going to make some H2O. So we would use up some H plus to neutralize the OH minus. So it's essentially like OH minus is sucking H plus away from our blood. Going to use it up. So we're going to lose H plus in our blood. Oh, okay, what just happened? There it is. Okay, so if we lower H plus, which way would equilibrium shift? To replace it, it's going to shift right. Almost done, guys. Okay, it's going to shift right because we need to replace the H plus that NaOH is taking away. So shift right. What's that going to do to the concentration of CO2 in our body? That will drop the concentration of CO2. If we're losing CO2 in our blood because we're reacting it with water so that we can replace our H plus, if we'll slow down our breathing, we can restore CO2 in our body. So here we're going to hypo to restore healthy levels of CO2. All right, I went 2 minutes over. I'm sorry. Anything beyond this will not